All right, Pirates, let's try to take two on these notes. I tried earlier, and apparently my iPad was out of memory, so that was 20 minutes of my time well spent. Anyway, we are beginning our next unit on waves. We have watched the episode of Cosmos. Hopefully you turned that in so I can give you some credit on that, in which they introduced some of the topics involved with waves. So we are going to take notes on slides numbers 1 through 8, which are the only slides available in your assignment. You are going to turn these in when done so that I can give you some credit on this and help everybody's grade up a little bit. So make sure you turn that in if possible. Don't forget to watch the two videos as well and to answer those questions so I can give you credit for those as well. All right, here we go. So what are waves? Well, waves are something that transfers energy, not matter, from one location to another. So they might use the matter that is available, and in fact, a lot of the ways that we're going to be talking about today do use the matter that is available to them in order to transfer that energy. So you see the picture down here. This is the most common wave that you might think of, and it is actually it is actually transferring energy from one location to another. You see, the energy starts off way out at sea, be it the wind or uneven heating of different currents, or even some seismic activity, and it travels all the way to the shore. As it breaks against the sand, it creates these giant waves. The energy gets compressed into very, very large waves, and that energy you can feel if you've ever been to a beach or seen a large wave. You can feel that energy as it pushes you back and up. So you can feel that energy. So water waves are an example of waves. Okay. Just like when you drop a pebble in a still water, you'll see those waves ripple out. The energy from the pebble hitting the water gets transferred out and diffused across the whole lake until it hits the shores. Another common piece of energy, another common wave, is sound waves. And you can feel that energy as well. If you've ever put your hand up against a speaker, you can feel the pressure as the waves propagate through. You can feel that energy pushing and decreasing as you hear that, especially in the bass frequencies. You can really feel those waves pushing against you. And then the last type is light. Light is a weird one. But light is an important one. It's one of the most common ways that human beings interact with the world. So we have water waves, we have sound waves, and we have light waves. The two most important ones we're going to be talking about is sound and light. However, water waves work as a stand-in or a metaphor for those other two waves. And so I'll be referring back to water waves as well. So those are the three most important types of waves that you will need to know. So why don't you write those down, and we'll move on to the next slide in a moment. You can pause the video if you need to. It'll need a little bit more time to transfer over. Feel free. While you're doing that, I'll draw a little shark down in the water. Dun, 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 dun. Okay. Moving on. All right, so there's two major types of waves. The first type of wave is what is called a, one moment, oops, I just lost my PowerPoints. There we go. All right, I just want to make sure I'm spelling it correctly. I hate when I give you the wrong thing. It's a transverse wave. And these are waves whose particles vibrate perpendicular to the direction of the wave. And that is the motion of the wave. And the major one that we've been talking about, and switching over to a little bit of a darker color and a little bit of a larger of a pen, is light waves. So light is an example of this. And water is also another example of this, light and water. All right, so we'll use water as the example, right? So here is way out in the ocean. Over here is the beach. So the waves are traveling from the ocean to the beach, right? They're traveling from the ocean to the beach, and as the waves travel, you can actually see the waves going up and down, and up and down. So you can see that wave there, right? And you can see that wave going up and down, up and down. That is perpendicular or at a right angle to the way that the wave is traveling. So the wave is traveling along the yellow line, but the particles are vibrating up and down or side to side. See? Up and down, side to side. Up and down, side to side. Water waves are the big example of that because you can see. And most of the energy that you feel if you ever go out in waves are the waves pushing you up and down. I mean, there is a little energy that goes from left to right, but most of that energy is going up and down. You can see that there is a large amount of water here, so there's a lot of pressure here. That's where the wave is the strongest. And in the trough, there's not a lot of water, so that's where the wave is the weakest. Okay, moving right along. You can pause that if you need to, copy everything down, and we'll move on to the next slide. That ink was a little too big, so we'll split the difference. Okay, the next type of wave is a longitudinal wave. Now, you don't necessarily have to have this memorized, but you should have it written down because you will have one more quiz left before the end of the year. It will be open note, so if you have these notes, it will be very good to have them. So you can just copy these answers down and get a good grade on it. All right, these are particles. They vibrate parallel to the direction of the wave motion. Okay, the waves are, best example of this are sound waves, one of our third example. These are longitudinal. Right, and if you've ever gone to a concert and stood up close to the speaker, you can tell that they are longitudinal, right? Because as sound goes this way, the wave goes this way, you feel these pulses of energy that whoom, 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 whoom. As it goes through, you get a pulse, you get a bunch of pressure, and then you have a light area, and then you get a bunch of pressure, and then you have a light area, and then you get a bunch of pressure, but you're not moving up and down or left to right. It's not forcing you side to side. It's not forcing you up or down. It's just feeling you. It's hitting you right in the face. This is how your ears work, actually. There's little hairs inside your ear, and as those pressure waves, as the pressure part hits your ear, you have these little hairs inside of it, and those get knocked down and sends a signal to your brain, and that's what causes you to process that sound. All right, I'll leave this up here for a moment. You can pause if you need to. Okay, moving on. All right, so there's these compression waves. You see these areas where the particles, the air particles or the water particles are compressed and they have a high amount of energy there. And then you have some areas where there's not a lot of particles. Those are called rarefactions. And then you have lots of pressure, and then not a lot of pressure, and then lots of pressure, and then not a lot of pressure. And so a couple of terms that you need to know are crests. Those are the high pressure areas. You can think about it as well as the high point of a water wave, right? We call those crests. So the top point of the wave is the crest. You see those over and over again. And then the areas where there's rarefaction happening, those are the troughs. The lowest point of a wave is called the trough. And then the average of those 2 points is kind of where we measure from. We kind of measure from that point there. But the highest point is always the crest. The lowest point is always the trough. And that leads to three different, and the only three ones that we're going to be talking about right now, the three different properties of a wave. And those three different properties are wavelength, amplitude, and frequency. Wavelength, amplitude, and frequency. And we're going to break those down one by one for each of them. All right? Wavelength is the easiest one kind of to measure. Wavelength is the measure of the distance between two similar points on a wave. Okay, the best way to measure wavelength is either going to be from the crest to the next crest, because that's the high point, so it's easy to find, right? You go until it gets to the highest point and then starts going down. That's one crest. You find the next highest crest, and then you just measure the distance between them. Or you can also go from trow to trow. And if you have a regular wave, what you're going to see is you're going to see that the wavelength is exactly the same. So if the wavelength from crest to crest is this distance, trow to trow would be about this distance, and if I took a ruler, I would realize that those are the same distances. Now, depending upon the waves, and we'll talk about the electromagnetic frequency next time we meet, but depending upon the waves, you're going to measure it in some sort of a meter. The biggest waves that we'll talk about are on the order of meters, but as we get down into the sound waves and the light waves especially, we're talking about nanometers, which is abbreviated as NM. And what that means is one of those wavelengths, the distance between them, is actually equal to this much. Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's how many meters it is. So it's really, really teeny. It's about the size, a little bit bigger than an atom, about the size of a molecule or a small unicellular organism. Okay, you can pause here if you need more time. If not, we'll advance to the next slide. Okay, next slide is the amplitude. The amplitude shows how much energy is inside of that wave, right? The bigger the amplitude, the more energy it has, and you usually, basically, it's the size of the wave, it's the size of the crest, or the size of the trout, right? So a wave that looks like this will have an itty-bitty amplitude, whereas a wave that looks like this has a much bigger amplitude. So the orange has a much bigger amplitude. The orange one has a much bigger amplitude than the green one, even though their frequency or their wavelengths are about the same. And frequency and wavelengths are related by a mathematical formula. We'll talk about it a little bit, but you're not going to have to memorize it. But you can see the bigger the wave, the more of the amplitude you have. For waves, the amplitude is how loud the sound is. So for example, you can have two notes that have the same pitch. The wavelength determines the pitch. It also determines the color. So here's what we can go back to wavelength for a second. You don't need to write this down, but in sound, the wavelength is equal to the pitch or what note it has, but in light, it's equal to the color. The color is determined by the wavelength. And so the sound, the wavelength is the pitch or the color. Also, we'll talk about it later, frequency, because they are related to each other, but pitch and color. Okay. For light waves, the intensity or the loudness of sound is measured in decibels. And for light waves, the amplitude determines how bright that light is. And that's measured in something called candelas, which, yes, is based in the unit of candles. It's how powerful a standard chemical or candle gives off, how much light a standard candle gives off. Down here we have some information for you to peruse. Anything more than a couple of seconds at these loudnesses, and the louder you get, the more damaging it is, so the less time you should be around it. You should maintain a distance of a loudness of about 85 decibels, which is busy city traffic. You can pretty much handle busy city traffic without damaging your eardrums for all day, every day, or 8 hours a day rather. Hair dryers, you can probably withstand a couple of hours maybe. Rock concerts, probably a couple minutes. Same thing with chainsaws. And iPad at peak volumes, maybe a couple seconds of that actually. That's why you should never turn your volume up on there, because that damages the ears. There's little hairs, like I said, in those ears, and the more stronger they get knocked over, well, the less likely they are to respond again later on, and that damage is permanent or semi-permanent. Okay, you can pause here, or you can move on with me. Okay, moving on, for our last slide of today is the frequency. The frequency is a measure of how quickly a wave is vibrating. Okay, for sound waves, frequency determines the pitch of the sound we hear. And audible frequency that most humans, as long as you haven't damaged your ears, is that 20 to 20,000 hertz. The lower levels are the low notes, those low notes that we hear. The higher frequencies are the higher notes. Dogs can't hear the low sounds as well as humans can, but they can definitely hear those higher sounds. We'll talk a little bit about what Hz means when we do a little bit of math. And then in light waves, the frequency determines the color that we see. And humans can only see a small portion of light. Here they are measured in nanometers. Remember, nanometers and frequency and wavelength actually are related to each other, so we can use that to calculate. But you have your low frequency lights, like your violets, and you have your high frequency lights, like your reds. Okay, that's it for notes. So make sure that you turn in once you get everything done. Make sure you turn that in. As a reminder, to turn in, all you have to do is click this arrow here, and then click Other Apps, and then click Share Note, and then click Schoology. Okay, and then Submit to Assignment, then Find My Course, and put it in the notes. Other than that, I hope to see you on Friday. I should be back in. Make sure you submit that, and go Pirates. Bye, guys.